Okay, so as requested, I'll go over the answers to this review. So we are discussing atoms. We're discussing wavelengths, frequencies, energy associated with those wavelengths and frequencies, and then also the electron, jumping energy levels and dropping back down again, like the flame test that we saw. So there are the equations at the top. I'll refer to those. I may have to scroll up and down to get to them. First question, a beam of radiation in the infrared region has an energy of 6.12 times 10 to the minus 21. When I rewrote this worksheet, I forgot to fix that. I just realized that. I changed the number and forgot to fix. So that may or may not be in there. We could check when we do the wavelength. All right, so what is the frequency of the radiation? So we have E equals H nu. So our E equals H nu equation, energy equals Planck's constant, H, which is a value right there, times the frequency nu. It's that funny looking V there. So we're given the energy, and we're given it in kilojoules. And if you notice, the H constant, Planck's constant, has joules, so we can't use kilojoules. So we got to convert that to joules. So we could do that preliminary step right here, times 10 to the minus 21 kilojoules. So using our marvelous ability to do dimensional analysis, we get 6.12 times 10 to the minus. Now we know 10 to the third would be 1,000, so 10 to the 21st. So this is going to be times 10 to the minus 18 joules. Or did I go the wrong way? No, that's right. Okay. So now we're going to use that here, 6.12 times 10 to the minus 18 joules equals Planck's constant, 6.626 times 10 to the minus 34 joules seconds, times nu. So just a little algebra, and nu will be equal to. Now joules and joules are going to cancel when we divide this over to this side, and the units are going to be 1 over seconds. 1 over seconds, remember, is hertz. And as we saw in Google the other day, his birthday, 155 years old. Old sucker. 6.12 times 10 to the negative 18 divided by 6.626 times 10 to the minus 34. If nothing else, you'll get good at doing scientific notation in your calculator. So 9.24 times 10 to the 15th. So a whole lot of hertz means a large frequency. All right, so there's the frequency of the wavelength. Again, 1 over seconds or hertz. What is the wavelength in nanometers? Let me just make a space here. So C is equal to lambda nu. Our other equation, wavelength is lambda, nu is frequency, C is that value right there, the speed of light. So C is 3.0 times 10 to the 8th meters per second. All right, so we know that equals lambda times, we just figured out nu as 9.24 times 10 to the 15th. Now, what unit do we want to use? Well, this is 1 over seconds. This is 1 over seconds. So our unit that we're going to have when we solve this is meters. So you have to make sure it's in hertz, or 1 over seconds. So now we're going to solve for lambda. So we divide 3.8, or 3 times 10 to the 8th divided by 9.24 times 10 to the 15th. So 3 times 10 to the 8th divided by that answer there, we get 3.25 times 10 to the minus 8. Now that would be meters, and then it asks for nanometers, so 1 meter, 1 times 10 to the 9th nanometers. Again, there's our conversion up there. So we're going to have 32.5 nanometers solving that, or 3.25 times 10 to the first. That would not be in the visible region. Remember, we can see about 400 to 780 or so. We see that chart coming down the lower here when we do that. Okay, so when an electron drops from n equals 3 to n equals 2, when an electron is changing energy levels, we have this Rydberg constant, n final squared, n initial squared. So where it ends up, the energy level that it ends up is the final. The initial is where it started. All right, so how much, notice I asked you in kilojoules. So a little bit of paying attention to the units, negative 2.18 times 10 to the minus 18 joules times 1 over. The final is 2, where it ends up, squared, so 4, minus 1 over the initial, 3, 9, 3 squared. So 1/4 minus 1/9, we don't have to do a common denominator because we're going to do it in decimal form. So 1 divided by 4 we know is 0.25 minus 1 divided by 9. However you can get that right, make sure you're getting that right so you're not putting the wrong numbers. So 0.139 is the decimal equivalent of subtracting those two. Times negative 2.18 times 10 to the negative 18th, the Rydberg constant, is negative 3.03 times 10 to the minus 19. This is in joules, so this is joules, which we want to change to kilojoules, so there are 1,000 joules in a kilojoule, so that's going to be equal to negative 3.03 times 10 to the minus 22 kilojoules. Notice it's negative. Remember, negative energy is meaningless. Energy is energy. That negative right there means that is released energy. So it's losing that much energy to the surroundings. Now, why is that important? Well, when you go to letter B, we don't want to use a negative value because it doesn't make sense to have a negative distance. We also want to go back to the one in joules. Why? Well, we're looking for wavelength. So what we're doing really is we're combining these two steps to find wavelength, because we have an energy, just like we did in the first problem, and we're asked to find a wavelength. Now, we can do two steps. We could do like we did here, energy equals h nu, solve for the frequency, then use the frequency to solve for the wavelength. But in the box here, you can, if you remember, I combined the two. If we rearrange this one right here, it would be nu is equal to c over lambda. So then E equals h nu, replacing nu with c over lambda, you get that equation right there in the box. So I'm going to do this one in that one-step problem by doing E equals hc over lambda, solving for lambda. So again, algebra skills. Remember, this is a joules seconds. This is meters per second. The seconds will cancel, the joules will cancel, and you're going to be left with your answer in meters. 3.03 times 10 to the minus 19th. Again, I'm taking the positive value of that. I don't want to have a negative distance. Equals Planck's constant, 6.626 times 10 to the minus 34. Times 3.0 times 10 to the 8th meters per second divided by lambda. Solve for lambda. So the first thing you would do is multiply both sides by lambda, because you want lambda on the top. Remember, common algebra mistake. We got to get rid of that from the bottom. So we have to multiply both sides by lambda, divide both sides by 3.03, and lambda equals. So it would equal 6.626 times 10 to the minus 34th times 3 times 10 to the 8th. So that's the top value divided by 3.03 times 10 to the minus 19, and you got 6.56 times 10 to the 7th. So 6.56 times 10 to the negative 7. Now that is meters, remember. Joules, this is joule seconds, 1 over seconds. So joules and joules cancels, seconds and 1 over seconds cancel, so you get meters. We want to change that to nanometers. So we're going to do the same conversion that we did up here in the first question. So this one right here, which is 1 meter is 10 to the 9th. So this comes out to be 656 nanometers. I'm not going to show the calculation just to save space. Now, right here is a chart you can see of the visible spectrum. So this says, can you see this photon? The answer would be, yeah, you can, because it falls within the visible range. It will appear red to our eyes, because it falls within the red range. All right, next one. Rank the following in order of increasing energy. Remember the foxtrot. We had ultraviolet bowl. He wanted an ultraviolet bowl. He ended up with a red bowl. His friend said, at least it's not infrared bowl. Remember, that's low energy. This is high energy. In the middle would be Roy G. Biv. And it doesn't matter if I put it over here for infrared and over here for ultraviolet, just as long as you do Roy G. Biv in the proper order. Well, it's always going to go red, infrared. So it's going to be Roy G. Biv this way. So that violet and ultraviolet. So low energy, high energy. Remember, energy and frequency are directly related. So high energy, high frequency. which means low wavelength or short wavelengths, or over there with the high energy. So the low frequency would be high wavelengths. And you can see that here. Red is 780. Violet is 400. So we have to rank these in terms of increasing energy. So the higher energy ones are to the left of the way I wrote it. You may have written it in the opposite direction. But just so you know that it's the high energy is the ultraviolet. Remember, infrared bowl, low energy. All right, so blue photon. So we have this guy right here. We have the infrared region. So we have this one right here. So now we got to figure out where these fit. Well, these are in nanometers, so the easy thing to do would be to change this to nanometers. So 1 meter, 1 times 10 to the 9th nanometers gives us 310 nanometers. So 310 nanometers is going to be over here somewhere, 310. Because you can see violet on our chart here is 400 to 720. So blue is about 440 to 490. And then infrared is going to be greater than 780, right around there. All right, so then this one is in hertz. Hertz is a frequency, so we're going to have to say C is equal to lambda nu, plug in the frequency, plug in the speed of light, and lambda ends up being equal to, and then we'll change it to nanometers so we can compare. So 3 times 10 to the 8th divided by, it's already in hertz, 7.18 times 10 to the 14th. And you get 4.18 times 10 to the minus 7 meters, which would be 418 nanometers. So 418 nanometers is going to fall, somewhere in here, 418 nanometers. If we look at the color, we're talking in the violet range. All right, so increasing energy. So increasing energy. The lowest is going to be the infrared. Next is going to come blue. Next is going to come 418. And then last is going to come 310. So they were actually right in the correct order. Duh. I don't know why I did that. What can I tell you? Okay, give the 4 quantum numbers for the 4 outermost electrons in zirconium. 5s2 and 4d2. So we're going to have 2 electrons in the 5s and 2 in the 4d. Remember, the first 2 columns are pretty easy. The coefficient is the energy level. And then L is equal to 0, 1, 2, 3 corresponds to S, P, D, and F. I'm going to print this, so let me get rid of that. So we are in the S sublevel. L is 0. When we are in the D sublevel, L is 2. M is negative L to positive L. So zeros plus a half, spinning one way, spinning the other way. Remember, if the first 3 are the same, that means they're in the same orbital, so you have to have opposite spin. Pauli exclusion principle. Minus 2 to positive 2, so minus 2 minus 1. Remember, they have to fill empty ones before they pair up, and according to parallel spin, they will be spinning in the same direction. 1, 2, 3, 4, 5, negative 2, negative 1, 0, positive 1, and positive 2 are all the possible values for M. And we would have 1, 2 electrons in there, spinning the same direction. All right, next one. What is the sublevel designation, i.e. 3s or 5f for the electrons with the following? Okay, so once again, L is equal to 0, 1, 2, 3, 4, 5, S, P, D, F, G, H. Remember, it goes alphabetical. All right, so if N is 5, L is 1, so that's a 5p. 3s, 5 and G, and then 8 H. All right, are these allowed? If N is 2, can L be 1? Yes, it can, because L is 0 to N minus 1. So it can be 0 or 1, and it is. And then M is negative L to positive L. So if that's 1, negative 1, 0, and 1, so that one is okay. 2, that cannot be a 2. It would have to be a 1 or a 0. And M can then be 0. 4, 3, negative 2, that one is just fine. 2, 1, nope, can't be a 2 because it can only be negative 2, or negative 1 to positive 1. So negative L to positive L. All right, so there's our review. I am not going to ask you any of the notes, any of the scientists. That will be on our test on Tuesday. And if you have any questions, be sure to ask before we take the quiz tomorrow.